What if the invisible force pushing the entire universe apart, the thing that makes galaxies race away from each other, could change over time? Imagine the very fabric of reality shifting its mind, and that choice deciding the ultimate fate of everything we know. Stick with me for the next 6 minutes and I'll explain what dark energy is, why scientists are baffled and excited, and what it could mean for the end of the universe. All in plain language with a few surprising twists you probably haven't heard. Here is my promise. By the end of this video, you all understand how we first discovered dark energy, the simplest idea for what it might be, a daring alternative that sounds like science fiction, and the real-world experiments racing to solve the mystery right now. Ready? Let's go. About 25 years ago, astronomers expected the universe's expansion to be slowing down. Gravity, they assumed, should be pulling galaxies back together. Then came a shock. Measurements of exploding stars called Type Ia supernovae showed the opposite. The expansion is accelerating. Picture throwing a ball and watching it speed up instead of slow down. That discovery flipped physics textbooks on their heads. It's like discovering your car's brakes suddenly turned into a turbo booster. Scientists gave the mysterious driver of that acceleration a name: dark energy. It's a placeholder for something we don't understand. Dark energy isn't light, and it isn't ordinary matter. It's invisible, but its effects are everywhere. The way galaxies cluster, the pattern in the cosmic microwave background, even how light bends through space all point to this strange presence making up about 2/3 of the universe's total energy. 2/3. In other words, the stuff you and I are made of is a tiny afterthought in a cosmos dominated by something almost completely unknown. That alone is jaw-dropping. The simplest idea scientists tried is called the cosmological constant. Einstein introduced it to keep the universe static and later called it his biggest blunder. Ironically, the cosmological constant is exactly the kind of thing dark energy could be, the energy of empty space itself. Think of space as a balloon with a hidden pressure inside. As the balloon expands, that pressure stays constant and keeps pushing outward. If dark energy is just this steady vacuum energy, the universe will coast into a slow, lonely stretch where galaxies drift apart and eventually we run out of things to light up the night. But physics rarely accepts the simplest answer forever. Enter a more dramatic idea: quintessence, a dynamic field that can change over time. Picture a ball rolling slowly down a landscape. As it moves, the push on the universe changes. That opens wild possibilities. Dark energy could fade away, get stronger, or even flip sign and become attractive. If it weakens, expansion slows. If it strengthens, we might face a cosmic disassembly. Which brings us to the big rip, the cinematic endgame. If dark energy grows relentlessly stronger, it would eventually overpower every force holding structures together. Galaxies would tear apart, then stars, then planets, then atoms. It's an extreme scenario, but the math allows it if the driving pressure increases without bound. Contrast that with the big freeze. If dark energy is constant, space keeps stretching, stars burn out, and the cosmos cools into a dark, empty future over unimaginable time. And then there's the big crunch. Only possible if dark energy disappears or reverses, letting gravity collapse the universe back in on itself. Small differences in dark energy-esque behavior today lead to wildly different cosmic destinies billions of years from now. How do scientists study something they can't touch? Clever measurements. We use standard candles, like Type Ia supernovae to measure expansion history, map millions of galaxies to watch how structure grows, and read the cosmic microwave background, the afterglow of the Big Bang, for tiny fingerprints. So far, the data mostly match a cosmos with something like a cosmological constant, but subtle tensions and mismatches between data sets keep physicists excited. When measurements disagree by a sliver, new physics might be hiding in that gap. Here's a mind-blowing detail. Quantum mechanics predicts vacuum energy too. So what's being done? New telescopes and surveys are mapping the universe in 3 dimensions: the Dark Energy Survey, the Euclid Space Mission, the Vera C. Rubin Observatory, and large spectroscopic projects are charting galaxies and their motions across billions of light years. These maps let scientists test whether dark energy changes with time or if gravity behaves differently on the largest scales. Some researchers even ask whether dark energy is a sign we've misread gravity itself, that Einstein's equations might need tweaking on cosmic scales. Think of a thought experiment, an alternate universe with slightly stronger dark energy. In that place, galaxies separate faster, stars form fewer heavy elements, and life might never arise. The cosmos is sensitive to tiny parameter tweaks, a cosmic butterfly effect that makes the question of why our universe has the values it does both scientific and strangely philosophical. Quick clarification: dark matter and dark energy are not the same. Dark matter pulls things together and scaffolds galaxies. Dark energy pushes the universe apart. Both are invisible and mysterious, but they play very different roles in shaping the cosmos. So what should you remember? First, dark energy is real in that its effects are measured. Second, we don't need to know what it is. That ignorance points to new physics waiting to be discovered. Third, how dark energy behaves determines the universe's long-term fate, from a slow, cold fade to a dramatic rip. And finally, scientists are actively hunting for answers right now, and every new dataset could rewrite the story. If this sparked your curiosity, tell me in the comments which cosmic ending fascinates you most: big rip, big freeze, or big crunch, and why. If you want more clear, surprising science like this, hit subscribe and ring the bell. Curio Science brings mysteries like this to life every week. For an optional deep dive, check the description where I linked recent surveys and a follow-up video about how telescopes actually measure cosmic expansion. Thanks for spending 6 minutes exploring one of the universe's biggest mysteries. The cosmos isn't done surprising us, and neither should you. See you next time.